Kelly, I've set it all. Should be just good to go.
All right, thank you.
Yep. Yeah.
Yeah. Oh, it's so sliding on broadcast. But I figured we can use our own laptops to do it.
Oh,
But it's being broadcast.
there. Okay.
Yeah, this is just for.
Oh,
Oh, oh, that's a good question. I don't know. But we can always get out of presenter mode, I suppose. You can give it a go. We can also show it out of presenter mode, I suppose. Oh, sorry. Look, I have to. I just got confused because I was Oh, you read it. Okay, sorry. So there was broadcasting. Okay. All right. I think we'll get started since we're already past the hour and we want to make the most out of this last session. So yeah, future directions. We've heard a lot of great talks this past week. Hopefully, oh, sorry. This good? Yeah. Okay. Yeah, hopefully, in addition to hearing like all the great talks and all the great science and all the future opportunities that we've heard of specifically today, we've also probably had a lot of great conversations outside of, just in sessions. And so we really wanted to like kind of continue off of that momentum with this last session. We want to stimulate discussion yeah, before I jump to the next slide with our key questions. Is there anything you want to
focus on the discussion?
Oh, it's off.
It's not.
Okay. Yeah, that's what I'm over here. You got that mic? I got this mic. Hey, Kelly. You really want to focus on the types of discussions that we can have between groups and the types of discussions that we're not already having within our own groups. So, and
We forgot to introduce ourselves.
And I'm Matt Dobbs. And I'm here at McGill and I work on CHIME and CHORD. And in my other life, I work on cosmology experiments like the South Pole Telescope and so forth.
I'm Kelly Gourdji. I'm based in Sydney. I work at CSIRO in Marsfield. I'm interested in radio transients, slow things like the radio afterglows and neutron star mergers to fast things like FRBs, and also sometimes things in between. Yeah. All right. So
and we value most the opinions of people, since we're talking about future directions a ways from now, the opinions of people who are currently working on their PhD, thinking about the PhD that their future students might write. So don't be shy if that falls upon you to speak up. Of course, other people's opinions are marginally valued as well, but don't be shy to speak up if that describes you.
So we're going to send you all on an intellectual treasure hunt. So we've come up with these, we've thought really hard about these 3 questions. We wanted to keep them kind of as vague as possible, open to interpretation, right? So the first one is, what is an underexplored potential synergy? So
hey, Ellie, do you mean a synergy between 2 experiments that are here in the room?
Thank you for asking. Yes.
Or between experimentalists and theorists?
I'm so glad you asked. Yes, both.
Or
Well,
between
things.
our wavelengths and other wavelengths?
You're reading my mind, Matt. And you can add any other ideas you have. I'm glad you found that funny. That's good. The next one, what's missing in your observatory's toolkit?
Are you talking about hardware?
Yes.
Do you mean those theorists that can't calculate things?
Also, yes. Yeah.
Okay, thank you.
And you can add in whatever you have in mind. And then lastly, Matt, you want to?
Yeah, and there's been a lot of talk today about what we should be looking for. And first, let's stop and just recognize where we are. There was a time not too long ago when we were all talking about maximizing N, and we wanted experiments that had more events. And now we're all thinking about the experiments we're designing in the future, which ones are better suited for what, but also even after we turn them on, what's the stuff we're going to throw away? And what's the stuff that we're going to spend Kendrick brains trying to tease out of the data? So we'd like to know what you'd like to search for most, what you'd like to keep. And we phrased it as, People always hear me say it. What is your Higgs boson? Because in particle physics, this was this thing that wasn't found for a long, long time, but it had this other characteristic that if you look for the Higgs boson and it's not there, you'll find something else of equal or greater interest. That it's a parameter space that even if the thing you're after isn't there, you're very likely to get rich mining in that area. So in particular, if there's no Higgs boson at the energy it's supposed to be, the cross-section goes to infinity and the universe explodes. So there better be something else there.
So what we'd like to do is just, I guess, divide the room into quadrants. So middle row, yeah, you can choose.
Adam, you're down. Yeah, you're down and you're right.
You mean
Marilyn, you were up and right. Steph, you're left. And Casey, you're up and left. Everyone's got the quadrants?
Yeah.
Oh, my right.
It's right here. It's right behind.
All of us had. So yeah, we'd like to give you like 10 minutes or so. They don't have to be these like long, paragraph long answers. Really try to synthesize it down to like, one sentence sort of bullet points. And then we're gonna reconvene. We're gonna call you all back together. And then I'd like to invite, I think our kind of rule of thumb was those who don't currently hold a PhD. We want to hear from ECR. This is going to impact you the most, these conversations. So we'd like to invite you, if you're comfortable, to just tell us what you've come up with, and then we'll go from there.
So for each of the top 3 bullets, you just have 3 one-line answers. So you don't have to justify it. You don't have to do anything. It's just going to frame the discussion, and then we're going to talk.
Okay. So team. We got way too much credit.
When you come back, we don't know what's
Exactly.
supposed to be like fun now that it'd be nice to see that.
And then he's actually
And it's so small that I don't know. But it's like, so we are building one hamster. And I can't get FRB, I can't get rid of my life. And so, and right, so we want to find what things go down below, and I want to find out if there's a long part kind of. Our customer and those. Yeah. I can hear at that time. I would be like I like the parties that people never
Yeah.
You want to create the nice things on our side. We have so much in the country. I have to be honest. We want to really sort of so if it's not with that, and I we don't give on the I like
There are 5 minutes. We're at 5 minutes. You've got about 5 more. You should be on your second or third question.
It's not needed, right? Like I think oh yeah, that's good.
That's why we want to. But it is very, like, I think that's not bad. It's
That stimulates for
yeah.
You're 5 minutes.
For a long time, we were something. So people want.
Gen Z.
Oh, definitely, because they. Okay, you're putting back in.
It's been.
So if we do edit something, you can just either go to the home screen and have you.
Maybe we can, yeah, just do, get out of presenter mode. Okay, I mean, I guess we can.
Why don't you suggest that they find their representative?
Okay, yeah. Okay, everyone. We're gonna start to get back into our places. Think about in the next minute, a representative that can give an overview of your answers to the 3 questions. Okay, great. Thanks, everyone. So I think what we'll do is, I think we ended up having 5 groups. That's all right. So I think what we'll do is just go around one question at a time. So we'll hear the kind of one-liners. And then once we get through them, we can unpack, or we can start with the first question, start a discussion, unpack that, and then move on to the next one. All right. Do we have a representative over here?
Yeah.
I was just.
You need to talk into. I was nominated. Oh, this is the last time I'll be able to do this. Since I'm defending in 10 days. So we were talking, my name is Alice Curtin. That's a good point. I'm at McGill. We were talking quite a bit, at least in the context of Chime. We had a lot of Chime members in our group about something that we think really addresses all of these, which is just triggering on things that we think are interesting. So something that we don't do, but we have the power to do is if there's a gravitational wave event, and especially now they talk about being able to identify gravitational wave events based on their precursor signals, or if there is an interesting gamma ray burst that is within our field of view, so just above in the northern hemisphere, we should just be dumping the raw voltage data for all antennas, and that it's a rather simple thing to do with potentially a very high payoff.
All right.
Thanks. Who am I throwing it to?
The youngest one they could find.
Thank you for that wonderful introduction. So we talked a bit about the first question in the context of fast optical coordinated observing in particular. So synergies between optical and like co-observing in particular. And I think one thing that occurred to me at least was that a lot of the new instrumentation is focused on finding the local FRBs, the closest ones, and so those are the most suitable for co-observing strategies for novel tests of emission and models for the source. So I think that's what's missing in our observatories toolkit might be like those new FRBs that are expected to come soon.
Great.
I think that's it. Yeah.
Yeah, thanks. So I'm Kyle. I'm a master's student here at McGill here, actually. So what did we talk about? As for like unexplored or underexplored potential synergies, one of the ones we talked about was efforts for co-detections across frequency bands, particularly between different instruments. Like Chime and DSA have our co-detections working group, which has been doing good work. As well as better one suggestion was a commensal survey at L band where we have good coverage with VLBI, so in the northern hemisphere, because ASCAP does it in the south. As for the toolkit, one of the suggestions that came up was better or the more use of coherent dedispersion, which addresses the detection problem, I guess, for high width and DM bursts. They have lower SNRs systematically in pretty much every instrument.
Great. And you can pause there because we're going around for each question.
Oh, we are?
But that's cool. Like,
I didn't
you
know
go.
that. Sorry.
That's excellent.
Oh, okay.
Okay, so pass it over to who's the upper right corner?
First question was unexplored potential synergy. Yes. Okay, I'm Jacob. I'm a grad student at Caltech. Yeah, I think we covered a few different things. One of them is similar to all the other groups, was sort of inter-observatory communication, so that triggering is even possible. I think that, we have VO events and the like, but something that's a little bit more consolidated, even just a database, like, if DSA 2000, as you've already heard, is going to be open source, from the jump. I think that would be it would be useful to have the infrastructure to actually be able to use that immediately and query that immediately, so that people who are interested in just any data product that's made available can immediately access that, and that's a non-trivial thing. We also talked a little about multi-messenger possibilities, other multi-wavelength possibilities. I think multi-messenger seems a little bit more complicated, or maybe not. Like Ice Cube came up, but maybe the energetics are just not quite there. But yeah, beyond that, yeah, I mean, data sharing is the ideal, but there's barriers to that. But ultimately, I think that should be the goal in whatever capacity is possible, given the funding.
Okay, last one.
Okay.
I'm Pavan from Swinburne. So we discussed a lot of things, starting with sort of so-called chime of the South. There's already a proposal to have all sky monitor called Casata, led by Keith Bannister, which would be super useful in terms of having doing multiple sciences, for example, pulsar timing, as well as FRB searches and whatnot. And one of the other things that we sort of were discussing was the blind spots that we have. We do not have a FRB detection, one-off FRB detection below 300 megahertz, or such events above 8 gigahertz, which would be extremely useful in constraining the emission mechanism, their surrounding medium, and whatnot. And I'll hand over to the next person to say the.
Hi, I'm Thomas Abbott, a master's student here at McGill. I think in terms of synergies, the only thing that hadn't been mentioned yet that we talked about was distributing or publishing our RFI for other observatories to study, and part of the benefit of that could be that some observatories may see something like we discussed. LOFAR sees satellites as RFI, whereas Chime Pulsar doesn't see those. And also potentially for training RFI mitigation algorithms, it might be useful to have a larger variety of known RFI. Yeah, I guess one thing to add is we also discussed that it might be challenging to convince people to publish RFI when they want to spend time on science instead. But yeah, that's for further discussion, I guess.
Okay.
Guys,
No, go ahead.
Do you guys want to continue on with the next question then?
I think pretty much everything was covered from our group. Is there?
Okay.
Okay.
Yeah, in terms of blind spots, it was mostly the bandwidth and the southern hemisphere. Those were the two major points, I think.
Great. We pass it down to.
We didn't really get past the first question. I guess what's missing is actually dumping the data for these other triggers. And having the ability to read the GCN notices straight into the Chime in an efficient way. Yeah. What? Oh, and I'm Lauren Rhodes and I'm at McGill. Thank you, Mason.
All right. I'll stop.
I don't want to throw it.
We didn't talk about this, but I guess implied by the co-observing is also publishing pointing information. So like this is something that's more common in maybe in the optical transient community, but we haven't practiced that yet in the radio community. So like for example, Rubin Observatory will be publishing their pointing location, and people just have the opportunity to follow if they're interested. Yeah.
Yes.
Alice, hello, Alice. So, and just a point on reading in the GCNs into Chime. So actually we tried this. Arvind was able to write a code to listen to GCNs and look at the Chime pointings, and also it was a one-day job. It's pretty trivial. It's just actually implementing online on the system was remaining. So it's there. It's somewhere on the repository. We have it somewhere.
Let's continue going around, then we'll revisit for. Is that all right? Or?
Yeah.
Okay.
Yeah, so I said the coherent de-dispersion thing already, so I won't belabor that point. I will shamelessly self-promote though and say that injection pipelines are very powerful tools for observatories to use in characterizing the biases in their populations and correcting them to the actual cosmological population that they can observe. So I'll that's my piece. I'll say that.
Yeah, going off of that, I think, yeah, I completely agree. Selection functions huge. The better that we can understand internal biases, I think the better for everybody. Beyond that, something Matthias raised was the capacity to track. I think like that, drift scans are amazingly useful, but if we can have sort of dedicated tracking infrastructure, whether that's adding to Chord, or using a DSA 2000 subarray, or something that can actually sort of do what is maybe more commonly like with ASCAP, like putting something like that in the northern hemisphere, I think would be amazingly useful. Yes, please.
Matthias, I just want to add, like in the dream scenario, you have Chime that is, you're able to rotate it fully. It's so infeasible, but instead of it just sitting there and staring up, you decide, oh, I'm going to rotate this whole thing to just start pointing to whatever source that you want or anywhere in the sky. Then you get the full detection rates along it. Like, I know it's not particularly mechanically feasible, and it's kind of on par with kind of say take like the GBT, but now you have all the back end of the interferometer. You have all of these beams that you're pointing to within that you can continuously track. It would just be like.
But DSA 2000 gives you that.
Yeah, that's true.
You got it. You just.
Yeah, true. You're right.
Do we go down or can others?
Yeah, has everyone spoken on the first 2 points?
We're missing this group.
Oh.
Oh, I guess we didn't have. I guess we didn't have a chance to talk about these.
That's all right.
One thing that I'd probably add was we did, and this is Pawan again from Swinburne, we did discuss about RFI information. So I know that RFI information exists for most of the observatories out there, but making them easily accessible and then making sure that it's widely available is something that would be a useful tool, I guess.
All right, should we move on to the final question? And then when we can open up the floor and did you want to start on this question since you have the catch box, or otherwise just keep it going to the next group?
Did you?
I think the previous points on finding the blind spots in luminosity period distribution, that is definitely the place where we will find the next Higgs boson. And we do not know exactly what happens at those higher frequencies or lower frequencies. And there are instrumental biases in our searches. And we know them, but we haven't gone past to that. For example, in PP dot diagram, because of instrumental limitations, the many of the pulsar searches were not done after a given point, both because of a combination of red noise as well as instrumental limitation. So searching for those things are possibly the places where we will find the next gem.
All right.
Try to do better this time.
I don't know if it was Barack part of that group or I don't know. All right, yes, yeah.
I think currently the sub-millisecond phase space of FRBs is completely a blind spot. And one of the ways to get there is to have, again, the single dish data, because if you want to go to sub microsecond, 100 nanosecond, it's single beams and you have to store the data and you have to go with supercomputers on them. And I think it also connects to another thing, which is maybe my Higgs boson. I think we don't know where goes the fine line between just a giant burst emitting pulsar and an FRB. And I think maybe pointing single dishes on close by galaxies and maybe trying to explore maybe a little bit more of the universe, but maybe the more extreme part of nanoshots of crab-like pulsars or the more extreme versions of that. Maybe that's missing.
Hi, this is Kenzie from MIT. On the topic of sub-millisecond width, I think it's like in the context of this Higgs boson thing, like looking for something and maybe finding something different. Like we know that there are microbursts, we know that there's nanoshots from pulsars, but we don't really know what the population is. So say we don't really find much. What I think is still valuable is that we'll have very tight constraints on like the dispersion measure and scattering at these high resolutions. So even if we don't find a new population of transients, we'll have a lot of really useful information by having data at those timescales on lots of FRBs too.
Great. Anyone from the last quadrant corner there? All right, Kyle.
Oh, someone catch, please.
Yeah, pretty much a similar thing as a sub-millisecond widths, all the way down to nanoshot analogs as well. I will say, like, there's a thought of we have this waiting time distribution, but the waiting time distribution, because of our search cadence, is kind of necessarily left censored. So if you search down, ever decreasing widths, like there could be extension of the waiting time distribution, at least a guess. I could be wrong, but I don't know, food for thought.
Yeah, this didn't really make it too far in our group. But personally, I agree with all of these points. I think like the searching for local analogs is can be immensely useful for actually disentangling the physics. Solving one thing that one thing that came up during lunch when Zarif, Dylan, and well, yeah, sorry. The point is I think that if we try and approach propagation effects problems with local analogs like pulsars, we get a lot further because we have so much more information. If we really use sort of that the availability of sources that we have now, which is going to skyrocket to actually sort of hone our techniques and then apply them to FRPs later. I think that can really push us forward when it comes to FRPs. But yeah, that's about it.
Okay, great. Have we done the rounds?
All right, I just want to, this is Sachin from McGill. I just want to add to less than millisecond width. We should go to the other extreme. Let's go to LPT and like that borderline where we go from coherent radio emissions to incoherent radio emissions, and all those, that parameter space is going to be really interesting, especially there are certain LPTs. To explain them, we need magnetars that should be older than like 0.5 mega years or something. That's insane, like based on how the magnetar evolution models are so far. Also, the twisted magnetic fields and things like what Alex Cooper and also Sam, I guess, who talked about the crustal. Those kind of things can be explored in that parameter space. That's very important. And also that's also the parameter space we could look for this binary systems, white dwarf binary systems, that how they evolve and how we can have transients in that phase space. So I'm promoting time slow basically here.
Great. I think at this stage we can probably open up the floor and just have free form discussion now that we've gone around. So I want to thank especially like our ECRs for giving your great ideas.
Can I?
Just one little thing I want to say that I had it up on the first slide but forgot to address it. But in like thinking about this and having these conversations, I also want to encourage everyone to think about like what expertise are we missing in the room? I'm not thinking of a specific person like by name, but just what sort of expertise are we missing to address some of these questions? Just something to keep in mind. And yes, go ahead.
This might go in that direction a little bit, but so like Sachin's work on simulating stuff like scintillation, I think I think that's extremely useful, at least for getting just some grip on the physics that's happening. Like I sort of think about like in galaxies, the sheer computational effort that's behind understanding galaxy evolution and the granularity, like the detail that we can probe with just purely computational work, I think is pretty remarkable. I think that's worthwhile.
So I'd like to add a few points on the theoretical advancements that are required. I believe that we are in an era where the theoretical understanding is lagging behind the observations by a lot. And this is going to get worse over the next few years to decades. So there has to be lots of theoretical advancements. And I would like to share something that other high energy probes do, which is they offer grants to do theory work on, say, Chandra theory or Fermi theory grants to develop theoretical models to understand observational data. I don't think we have anything similar within the radio observatory. I don't think any radio observatory offers theoretical grants or any such support to do theoretical work. But at the same time, most of these observatories, they also use huge computational resources to reduce and analyze their data. I was wondering if it would be possible to share some of these computational resources with theorists who want to do some simulations. Even just few GPUs would go a long way to do some simulations. It would accelerate our theoretical understanding of many processes. So could a program be initiated where theorists write proposals to ask for computational time on maybe some of your GPU, the hundreds of GPU clusters that many observatories flaunt to use for a few days to advance theoretical understanding. So,
Really great point.
Yeah. So we'll go back here after, but just a comment for how it works in Canada, which is that none of the collaborations have computer time to do analysis. That's all provided after the fact by a national organization. And we win that time competitively with proposals. It's not money, it's cycles on their computers. And a little secret is that if I collaborate with someone outside of Canada, I can share my time with them as well. So, you know, if people really, really are starved for the thing that people in this room, at least that have some Canadian ties, need, there is some computing accessible. Sharing the GPUs on the telescopes is really challenging just because of the logistics involved with uploading software and firmware and so forth. But there certainly is the possibility here. Let's go back here and then we'll go online. Or was the online first?
Well, my comment was more a slight change in topic. So if it's relevant to anyway, yeah. Sorry, this is Adam Lamon, MIT. Just to the Higgs boson question, I guess the phrasing there made me think of something that is a missing piece of an otherwise complete puzzle, and so I think something that should be put on that list is the use of FRBs for fundamental cosmology, which was a topic that came up a bit through the conference, and in particular the potential of lensed FRBs for H0 measurements. But that's, I guess, one application. But a lot of the other, as I understand it, the cosmology gold really require the high Z FRBs, which is a challenge both to detect and to localize and get distances for. And I think a missing bit of expertise is in how to really structure that kind of survey to get that sample and do that kind of work.
Great. You meant high Z.
Yeah, high Z.
Let's go online, and in the meantime, pass the box up there.
That's right. Okay, Sunil, would you like to unmute?
Sure. Yeah, this relates to the point of what kind of expertise we would love to have in addition to the people already present here. So I particularly am excited about using probes, various probes of foreground gas, and FRBs are included in them. So synergies between like quasar absorption and FRBs, and maybe X-ray emission and FRBs, and SZ effect and FRBs. I think these areas are what could be super exciting in the very near future. And so, yeah, I particularly would love to see an FRB detected from a host galaxy of a quasar. So there we would be getting, for the same sightline, essentially, both information about the ionized gas and the neutral gas through absorption measurements. So, yeah, I guess this is a direction that I would love to continue thinking about, and along with others in the field.
Some ideas for invited speakers for FRB 2026, perhaps.
Sorry to comment on that. It's Ilya here. It's actually very easy to decide whom to invite. You invite X, he can talk about both sides. I just want to go back slightly in time to that comment about the computational resources. I'm not an expert here, but I just want to ask you, is there a room to do citizen science with FRBs? Like there were some cases with like astroparticles, I think. So maybe we can use this.
Seems to be.
Well, okay.
You want to go in the middle? Adam, do you? What am I doing?
Oh, okay.
Brian Gangsler, UC Santa Cruz. So some of the FRBs that will be published in Chime FRB Catalog 2 are citizen science FRBs. So I had a project called Burst from Space that was worked on by a bunch of people, some of them in the room, but particularly by Mark Walmsley. And that, I forget how many, but it was like hundreds of thousands of bursts, maybe. Every one of them has been, the waterfall plot's been inspected by 10 citizens. And all the highest scoring ones that I think got more than 8 out of 10 people saying it was real were given to our czars. And most of those, they also agreed they were real. And so the ones that are in Cat 2 is just a tiny subset. They're just the high signal to noise ones, I believe. But there's quite a lot of them, including some at high DM, and there's lots of work needed to analyze them properly. But the bottom line is that you can lower your signal to noise substantially and let through a lot of candidates and eyeball all of them, because there's people on the internet who are super enthusiastic about this and will do it very quickly.
Maybe this is to you, Martin.
Yeah, Martin Topinka, Cagliari, Italy, enough again. Back to that Higgs boson. I'm actually like interested in or excited about having like loads of new FRBs, which actually means something like a big data amount of events, and it's also always like a good opportunity to look for like a very rare cases like outliers. Like, and I will be super excited to see some like new physics manifestation, like whatever, like evaporation of primordial black holes interacting with the environment, or cosmic strings, or something as weird as I don't know, quantum loop gravity proofs or something like that, even if it's like a tiny fraction of the entire sample.
Did we have a question or comment from Sunil online?
Oh, it was basically what Brian suggested, so I lowered my hand.
Okay.
Yep.
Thanks.
Yeah, I have a couple of comments, and I'm sorry because, oh, sorry, I'm Stella. I'm from Caltech. Yeah, so I have 2 comments that are kind of covering different parts of this, so I apologize. First, I just wanted to reinforce Sunil's point. I think it's really important to stay humble about what FRBs cannot do. And I think, you know, when we talk about, say, solving feedback with FRBs, we have to be realistic about the fact that FRBs will not actually solve the physics of feedback. They might tell us where the baryons are, but they won't tell us how those baryons got there. And that's where other probes like SE, quasars, et cetera, become really important. And I think one of the biggest holes that's not useful about FRBs is that they don't tell us anything about kinematics. And that's exactly where turning to other wavelengths becomes really useful. And then my other comment, more on the Higgs boson side, is that wouldn't it be amazing if in 100 years we had a whole pulsar population that was known in M31? You know, FRBs are great, but imagine if every FRB was actually behaving like a pulsar. Our lives would be so much easier. So I just, you know, I think also pushing for extragalactic pulsars, you know, there are searches already happening with FAST, but arguably we probably need even bigger and better surveys to do this. It would be hugely rewarding and would also, I think, be very important for understanding FRB sources as well.
This is Ziggy Kleunens, University of Amsterdam. My Higgs boson is finding a star at the position of an FRB. I think that will really help figuring out the sources, especially if you can get radial velocities and figure out if it's in a binary. Related to that, it's really great that so many astronomers who are interested in galaxies have been coming to the meeting, but I think it would be nice in the next few years if there's more people thinking about stellar evolution also joining, and to go from the sources to the progenitors of those sources and figuring out the whole life cycle towards making an FRB. That was it.
And my Higgs boson would be to look for millisecond duration coherent radio transients from non-neutron stars, targeted or monitoring of non-neutron stars, and searching for millisecond duration radio transients, be it white dwarfs or even different planets or black holes. And there are many other sources that are capable of emitting millisecond duration radio flares. And studying or monitoring these non-neutron stars can inform us a lot about these emission processes in different systems, which could inform us about FRBs ultimately. Maybe if we find FRBs coming from black holes or white dwarfs, that's a Higgs boson. If we don't find such bright FRB-like bursts, and if we still find millisecond duration other coherent radio emissions, that's a completely different engine with a completely different magnetospheric properties that would still inform us a lot about how radio waves can be generated in different environments and how they can propagate from them.
And populations.
Yeah, exactly.
Hi, Ayush from the University of Toronto. I think while astronomers are great in terms of who's missing in this room, if we're going into an era of big data, if we're going to have DSA 2000 and we're going to have LSST, I think we need people to develop infrastructure. So if I have a grad student in the future, I want them to be able to go online and download all of the relevant data and analyze it either directly on the web or spend less than 1 day doing that. And I think we need people developing that infrastructure to actually allow us to be efficient in our science.
You have Adam here.
Hi, Adam Dong from NRAO. So my Higgs boson would be finding a galactic analog, whether it be a neutron star, whatever, that doesn't have a period. Because FRBs don't really have a period, so you need something close by, like SGR 1935, for example.
Jason?
Very quickly, there's a paper by Reshma Anatomas, a source towards the galactic center, coincident with a Fermi gamma ray source that shows a bunch of 100 millisecond wide pulses, but no period.
Delete.
Oh, and delete, yeah. I am Jason Hessels from McGill.
I did want to ask a question about about community served baseband dumps. One of the main things that people talked about in the first section was the ability to grab data from a telescope that hasn't triggered from a trigger from somewhere else. What is the maximum time period before and after you send your notice that the baseband buffer needs to be? Does it become unuseful when it's more than 100 seconds? Do we need an hour?
Do you just mean in general?
Yeah, like in terms of all these things, like right now, in most of our big survey telescopes, we have a baseband buffer that's 100 seconds long-ish, order 100 seconds. If you don't ask for a trigger there, it doesn't matter what we decide, you're not going to get it. And that's just a matter of money. It could be much, much longer than that. And so the question is, like, is that 100 seconds adequate, or, you know, do we need a lot more than that?
Just yeah, so I'm Molson here from McGill, and just as an initial reaction, the feeling that I get is that that's very unbounded, that parameter. Like, we just have no idea what the relevant timescale for coincident triggering is. Like, yeah, but moving on. I think we have over here. Let me.
Hey, Barak Zakai. I think my point is almost similar to yours. To me, your question is an FRB a predecessor to something? And if that's the case, then indeed you need to have some estimate for the timescale. Who knows what it is? And if you can save the data longer, do it. But you know, let's plan this.
We should only be wrapping up here pretty soon. So
I'm not an optical astronomer. This is Calvin Leong from UC Berkeley.
I just looked up what the Rubin cadence is, and I think you can classify whether something's an optical transient on the scale of an hour. So an hour is a pretty good time scale. And we are all talking about following up our radio detections with optical telescopes. That's really hard because optical telescopes don't have a huge field of view, nor are they very sensitive if you have a lot of time on them. But we actually have LSST, and if we were to just shadow LSST with our radio telescopes, we'll know whether in an hour, whether you want to trigger on it or not.
And incidentally, that's kind of the time scale of the next job. Well, if you were there to base that.
Alice Curtin. For someone who spends a lot of time looking for FRBs coincident with gamma ray bursts and thinks about gravitational waves as well, I think the baseband buffer times we have already are quite sufficient for this. There are models, and I'm not a theorist, I'm an observer, but there are models that predict you could get these coincidences centuries before, but most it's that millisecond before the merger when your FRB would be produced. So we don't need hundreds of hours or hundreds of seconds, maybe hundreds of hours is unrealistic buffers.
Lisa will be able to help with those, right? We can just point our sensitive telescope exactly when we know the thing's going to merge.
So maybe we'll take these 2 questions and then close out the session.
Okay, this is Kenzie from MIT. Something that I think would be interesting is if we can connect FRB persistent radio sources to persistent radio sources independent of FRBs and maybe connected to some other transient or something else in the universe. Yeah. Okay.
Marcus Lower from Swinburne University. On this topic of Higgs bosons, if I was to suggest one, it would actually be the instrument to find the Higgs boson, so the LHC in this case.
Yeah.
Instead of being, we've heard a lot about low frequency aperture arrays. What about high frequency aperture arrays? Like the Embrace idea that was proposed for the SK mid back in the day. Or even better, that was an L-band aperture array, even better, an S-band aperture array. I know those are very difficult things to construct. The cost per element is very high, but I think it pays to be a bit ambitious, especially thinking about a very future forward thinking instrument that could do a lot. Thinking about things in the galaxy, you don't need to worry so much about the interstellar medium. Don't need to worry about scatter broadening. Dispersion isn't so much an issue. And that's the main thing. And also you're looking at a slightly different parameter space. All these old sky monitors, they're focused at low frequencies. We don't really know what's going on at high frequencies.
But isn't it weird that SK having an S-band?
No, those are dishes. This would be an aperture array that can see the whole sky, can point anywhere. And with my pulsar hat on, you could also time all of the pulsars above the horizon.
Wrap it up?
Great, yeah. So I think that's all the time we have. I do want to emphasize that, speaking of time, we're in a very special time. There's so many new instruments being designed, optimized, and put together right now. Many of these are funded. Many of them are being bolted together. And most of them, their engines, their brains are the software behind them that's still relatively easy to change. We've all experienced how hard it is to get our friends and colleagues to change anything for a working instrument. And there is this special time right now where you can get people to try new things and look. And very often, and there's going to be one more comment. And very often people are willing to look in the early prototype stages. And it's super, super influential if you tell them what you're after, but also you send them an email with like a one-page-ish highlight of your crazy idea. It sticks in your mind, you come back to it, you think it's wrong, you ask someone again, you come back to it, and you might actually look there. So yeah, don't hesitate to dream and tell people about it. Okay, one last closing comment from online from Shaman.
Sorry, I didn't mean to jump in on your closing comment, but I just wanted to draw people's attention to this relatively new thing called ODS, observatory data sharing, which is an API-driven approach to letting other people know where an observatory is pointing its radio telescopes. This is primarily aimed at coordinating with satellite operators to avoid bore site directed RFI. Starlink is coordinating with the VLA right now successfully. And we are hoping that other observatories will adopt this standard and other satellite operators will adopt this standard. The more people adopt it, obviously, the more valuable it gets. But it also addresses the concern some people mentioned during this session about being able to co-observe by knowing where other people are pointing. So that's just something I wanted to point out to people who don't know about it yet. If you look for NRAO and ODS, you'll find it fairly easily.
Thanks, Shami. Yeah, to close the closing, I just want to thank everyone, especially the ECRs, for sharing your thoughts. I think we've also come up with a lot of tangible ideas, like things that can be achieved within the next year before the next conference, which I think is pretty exciting. So we'll share these slides and hopefully, serve as a reference point to recall what we talked about this afternoon. All right, I think we can finish up.
Okay, you can hear me? Well, I think I guess I'll just speak on behalf of myself for a moment. I'm very honored to be doing this. The